to the 2,339th meeting and tonight's lecture on defining fundamental constants of nature. And it is my pleasure to introduce tonight's speaker, David Newell. David received his BS in Physics and BA in Mathematics from the University of Washington and his PhD in Physics from the University of Colorado. He did postdoctoral work on the Watt Balance Project at NIST, on an NRC fellowship, and then joined NIST as a staff member. He joined the Code Data Task Group on Fundamental Constants at NIST and worked on the 2006 and the 2010 adjustments to the international standards for the fundamental constants. Currently, he's working on the 2014 adjustment of these values and on the construction of a new Watt balance that will allow the kilogram standard of mass to be defined in terms of the fixed value of the Planck constant. David is a recipient of the NIST Stratton Award for his contribution to reducing the uncertainty in our measured value for the Planck's constant by a factor of 7. The Department of Commerce Silver Medal for innovations in nanonewton level force measurements, and the Department of Commerce Gold Medal for a landmark measurement of the Planck constant, leading to a new definition of the standard international unit of mass. David is a member of the American Physical Society and chair of the Code Data Task Force on Fundamental Constants. Please hold questions to the end of the lecture and join me in welcoming David to the podium. David.
Well, I'd like to thank Larry for the invitation to be in front of you tonight. Really enjoyed the evening. I hope I can continue entertaining you with my presentation. I'm going to talk about defining fundamental constants in terms of the new International System of Units. I will continually fall back and call it the SI. It's the International System of Units. An outline of my talk, I'm going to give a brief history of measurements, very brief. I want to introduce the concept of a universal measure forming the foundation of your measurement system. I'll then go into the new SI, introduce what is meant by what is a fundamental constant, how we would form a system of units with the knowledge we have today, the paradigm shift from the present SI to the new SI, and the impact, consequences, and advantages of going to the new SI. I'll then wrap up with trying to communicate and efforts to communicate the advantages of the new SI to a variety of audiences, the general audience, educators, and hopefully some manufacturers. So for a better brief history of SI, I recommend Jeff Williams' very short but really nice article, Defining and Measuring Nature, the Make of All Things. It's a really nice read. I get my history from a more simple source, and that's the comics in my local newspaper. And during the 2001 NIST Centennial, there's a comics in the Washington Post called Flashbacks, and Patrick Reynolds ran a series on NIST during its centennial. It started with the history of measurements and then the formation of the Bureau of Standards that then became NIST. And what I found interesting about this is his very first panel shows that we've been making measurements ever since we existed. The first one shows, a cave dweller, measuring, Junior with a stick to fit him to his deer skin. So we were constantly making measurements by observing and judging our surrounding environment, how far that ledge is before I fall off, how large this thing is. So it's an innate sense that we're always making measurements. Here's another person with a stick making a measurement. He's judging the velocity of this sphere coming at him at roughly 40 meters a second and the spin of that object and trying to judge where it's going to be in the next split second with relationship to the stick that he's holding. I would argue that not only is this a measurement, but this is a precision measurement. And a field of precision measurements that if you mastered is far more lucrative than some of the other traditional fields of precision measurements. So the next panel goes into the first ancient agricultural civilizations and showing how, in order to start commerce and trade, they needed a system of standards and weights to actually trade. Now, what's interesting of almost all these ancient societies is that they had a universal measure. It was either a grain or a seed. Shown here is a seed of the carob tree. And that was the universal measure, and you took a number of them, either 5 or 6 or 7. You put them in a line, and that gave you a longer length, and you built up upon length. You take the length and square it to get your area or your volume, or number of the seeds for your volume or mass. But this was the universal measure of these ancient societies. So he goes on, and he goes through how the dominance of the Roman Empire was somewhat the first standardized international system of units, some of the units still being used today, how new technologies such as electricity necessitated the formation of new measurement techniques and developing new standards, and how local industries needed to form their own standards in order for interoperability and compatibility with other systems and world competition. Here it shows, this is about the Baltimore fire. You know, Baltimore was burning and local towns sent their other fire engines and stuff there, but the couplers didn't fit, so they just all sat there and watched Baltimore burn down. Sorry if you're from Baltimore. And then finally, he talks about how NIST and other national metrology institutes form standards, not just for the basic standards, but very useful standards for all industry. In particular, as I go on, I'll be talking about 7 either base units or 7 fundamental constants, and you may want to ask why 7 and why not 4 or 3 or 2 or even 1. And the reason is because we need to develop standards for all of industry. So like the lighting industry, there's a candela base unit, which I won't go into. So let me get back to the concept of a universal measure. In a proposal by John Wilkins in 1668, he proposed a system, a decimal system. Now that wasn't new. The idea of decimal systems has been around. But he chose his universal measurement as time, and he chose the 1 second. And from time, you can derive a length through what's called a seconds pendulum. You make a pendulum a certain length, and it would take 1 second to swing one way and 1 second back. And with the definition of the second, you could then get your length. And then you get your area and your volume and your mass. Well, unfortunately for this, they knew that here's the relationship between time and length, and you have the local acceleration of gravity, and that varies by as much as 0.5% depending on where you're on the spinning Earth that we're on. So that was a limitation to this universal measure. But it's interesting to note that, that this technique was turned around, and all the way up to the 20th century was used to measure gravity. So you'd have a time and a length standard, and you could back out your local acceleration of gravity. And shown here is a Cater clock doing just that. This is a reversible pendulum. You got your time standard and a precision optical measurement where precisely your pendulum is when it swings. Various natural philosophers and savants at the time picked up on that idea. Gabriel Mouton suggested, again, a decimal system, but a length as his universal measure. And his length was going to be a certain subdivision of what was considered somewhat at that time and invariant to nature, and that's the Earth. So it would be a certain fraction of the meridian, and of course the meridian running through Paris. Various surveys were done of the meridian through Paris, and the latest was by Delambre and Michon, and they went from, well, one went from Barcelona up to Dunkirk, and the other way around to measure precisely that dimension, and extrapolated to how far it was from the pole to the equator of the Earth. Now, I put down this article here by Ken Adler. This is a fantastic story, really, because they're marching through here. This is during the French Revolution, and France was at war with several countries, including Spain. So they had to get the go-ahead from both generals, and they had to cross over the boundary of conflict. Sometimes they were held because their survey flags were white, it looked like the monarchy, and some of the local countrymen didn't like that. They had to go through Paris when people were being beheaded at the time. So as a metrologist, when I think I'm having a bad day, I just got to think about these poor guys, and I have nothing to complain about. So the measurement was made, and it was the birth of the metric system. That was the definition of the meter. And then from a cubic decimeter of water came the first kilogram of the archives, or the kilogram of the archives shown here. So let me fast forward through the evolution of the SI. We're right here, 799. This is the birth of the metric system. We have a mass unit and a length unit. We can get everything from that. In 1875, 17 members of the nations signed the Treaty of the Meter to formulate a new international system based upon and start forming new standards for the meter and the kilogram, along making platinum iridium standards. They formed three entities. The first was the General Conference of Weights and Measures, the overseeing governing body that made decisions on the system that they were developing. That's the CGPM. The International Committee of Weights and Measures, the CIPM, that provides technical input to the CGPM, and I'm sorry for all the acronyms. And then the BIPM, the International Bureau of Weights and Measures, that provided traceability to the system. And in 1889, the first conference made and accepted prototypes for the meter, kilogram, and the second was based upon the mean solar day. Fast forwarding up to 1954. So back here we had the base units, a meter, kilogram, and second. In 54, we adopted three more base units, the ampere, Kelvin, and the candela. Now, if you go back and you actually look at the definition of the ampere, you know, it's two parallel lines, wires, 1 meter apart, infinitesimal cross-section, infinitely long with 1 amp each. They would have 2 pi times 10 minus 7 newtons per meter length on it. If you shove the equations in there, what that really says is mu naught, the permeability of free space, is exactly 4 pi times 10 minus 7 newtons per ampere squared. It defines a fundamental constant exactly. So the system's already evolving towards a set of exact value of fundamental constants at this point. In 1960, the official name SI, International System of Units, is adopted. Moreover, the meter is redefined in terms of a invariant of nature, and that's a particular wavelength of krypton 86. Fast forward to 1967, the second now is defined in so many oscillations of a cesium atom, a hyperfine transition. And in 71, the mole becomes the 7th base unit to help out the chemists and the chemical industry. 1983, the meter is once again redefined in terms of the speed of light, of velocity. And so here we are in 2018 about to revamp the whole SI. So here's before we go there, here's the present SI. I'm just showing this here. So we have 7 base units on base quantities. So we have time, length, and mass. And we have particular references to time, length, and mass, the second, meter, and kilogram. And they are defined at particular points. A kilogram is the kilogram. A meter is so far, how far light travels in a particular time. And it suggests a particular experiment and a particular value. And those values are sort of what we're used to. You know, a bat being a meter long and a ball being roughly, you know, 1/10 of a kilogram. Let's go on to the new SI. I want to tell you what fundamental constants are, how to make a system of units with our current knowledge, the paradigm shift, and advantages, impacts, and consequences. Now, the idea to base a system of units on fundamental constants is not new. James Maxwell noticed that to obtain standards of length, time, and mass, you could use the wavelength, period of vibration, and absolute mass of these imperishable and unalterable and perfectly similar molecules, entities that are the same anywhere, anytime. That's another important thing of a universal measurement. A universal measure. It's available to everyone, anywhere, anytime. And likewise, Max Planck in 1900 said two constants. Now he's talking about, what wasn't really called these at the time, but Planck constant and the Boltzmann constant. And through the radiative entropy equation, a system of units for length, mass, time, and temperature for all time and all civilizations. You could back out those quantities from just Planck constant and Boltzmann constant for everyone, including the extraterrestrials. So, they exist everywhere. So let me tell you what a fundamental constant is. A fundamental constant is a parameter in the equations that describe the basic laws of physics as we understand them today. It's a parameter. So what do I mean? Here's a basic law of physics that we accept. It's Newtonian's universal gravity. And it's observed that there's a force between the product of two masses and the distance between, inversely to the distance squared between them. So you can measure this, test this equation by some apparatus. You have a torsion balance, you see a deflection of the masses as they come together, and you have an independent measurement of the restoring spring constant of the fiber. And you can get a method a number out of it, as Cavendish did back in 1798. And you get a number for this constant out in front. And what's important to note here is that this constant has dimensions on it. We're using these constants that have physical dimensions for physical measurements. And you can base it in the system of units that were used at that time, meaning the MKS, meter, kilogram, in seconds. There are other fundamental constants from other basic equations that we accept. It was observed there's the same inverse square law from Coulomb interaction. So there's some constant out in front of an observed force of a product of two charges divided by their distance squared. I chose the Biot-Savart law, but for magnetostatics, there's a field generated by a constant current, and it's proportional to another constant. Call that a magnetic constant, if you will. Maxwell's equation related the speed of light to those two constants at that time, and general relativity related the speed of light as a conversion factor between energy and mass. Planck's relation related the Planck constant as a conversion factor between energy and frequency. The Rydberg-Ritz formula was an empirical relation between hydrogen spectra, the inverse of the wavelength of the spectra, to the difference of the square root of just numbers. And there's something out in front of here that was constant. The Bohr theory of hydrogen showed that the energy equivalent in state of his basic theory was the energy equivalent of the mass of electron divided by that state squared, with a collection of constants out in front, when taken together, are dimensionless, and turns out to be the fine structure constant. So I introduced these equations, and the fundamental constants start showing up in several different equations, and this is very powerful because then you can perform different experiments for the same constant. Here is comparing theory and measure value for the speed of light. You can actually do a time of flight measurement within your system of units, but you can also go back to the basic force equations, measure this is permittivity, so we're doing electrostatics, getting a value of permittivity of free space. You can do magnetostatics and get the permeability of free space, and then calculate the speed of light and compare it to your time of flight measurement. And if they agree, then you know that your understanding of the physical world much better, and you believe that that value of the constant is indeed constant. Hydrogen spectra, you compare it to actual measure values of the mass electron, the elementary charge, and Planck constant, and test this relationship. And it's interesting to note that Bohr himself said this relationship may be actually used to get better values of the mass electron and H and the charge of electron, and that indeed has turned out to be the case. Going forward, here is comparing a variety of different ways of measuring the fine structure constant. This is for the 2010 codata adjustment, but it's just showing different experiments in totally different, unique ways, getting different values of the fine structure constant and comparing and see how well they line up. So you have a gyromagnetic ratio measurements, either the proton and helion contributing. We have the hyperfine transition of muonium with a little bit of theory, but you have a alpha, a fine structure constant in there. You have condensed matter physics with von Klitzing constant related to the fine structure constant. You have this relationship of the Rydberg, that's this guy, but then you have measurements of H over M, which are actually recoil measurements of an atom from absorbing and emitting the photon that gives you a fine structure constant. And then you have a measurement of the anomalous moment of the electron and QED theory that will give you a value of the fine structure constant. And so as these agree or sometimes not agree but get more precise, we have a better understanding of the laws of nature that we accept as valid and a better value for the fundamental constant. So how do you make a system of units? Let's back up. You're using this system of units for physical measurements, okay? You're going to start with all the quantities that you know. And so I have the simple example that just has 6 quantities and the physical laws that relate these quantities. So shown here are 6: force, mass, acceleration, velocity, time, and length. And the relationships are just Newton's second law and simple dynamics, okay? So you choose you need to choose an independent subset of the base quantities that will then form the foundation of your system of units. So for this set, you need to choose either force or mass in any 2 of the remaining 5. So the obvious choice, if growing up in physics, is a length, mass, and time. But you're not done yet. You still need to choose a particular reference for these base quantities, and you can choose it in terms of a unit. So the length is 1 meter, the mass can be 1 kilogram, and time can be 1 second, being so many oscillations of cesium. Here's a hunk of platinum iridium and time of flight. Excuse me. If we took our understanding of the laws of physics today, there are other equations, in particular the energy equivalent relationships that have out in front these constants of nature that have dimensions in them. And we can choose those as our base quantities because in this example, the Planck constant, speed, light, elementary charge, and Boltzmann are all invariants in nature that have dimensions. And they have a particular value, and we can choose those as our basis. And they are available to everyone, anytime, anywhere, if we agree upon the value that we assign to them. Now the paradigm shift between the present SI and the new SI is that the present SI is defined by the unit, something that we're familiar with, length, time, and mass. And there's actually 7 of them, and they have definitions. You know, the second is so many oscillations of a cesium clock. All the other units in the SI today are then derived from these base units, okay? When we go into the new SI, we're going to define 7 fundamental constants as exact, and then all units are realized from these constants. So what's changed here? There are no base units, and with that, there's no definition of base units. There are just these exact values from which you can get any unit. So here's a present SI again with the base unit and the base quantities, which we're somewhat familiar with and we interact with as we make judgments all the time. Here's the new SI. And I'm showing this because of 2 reasons. So here's just the constants, and we just say, the unperturbed ground state hyperfine splitting frequency of the cesium-133 atom is exactly this number of hertz. And that's it. And that's a formulation for all the other 6. These numbers are chosen to be for continuity going from the present to the new. You don't have 1 here, otherwise you have a big shift. You can be a theorist and choose H equal to C equal 1. There's nothing wrong with that, but it won't match up with the current values of the units today. The other thing to note is the base quantities. It's no longer length, time, and mass. It's something that we're not used to thinking about. It's frequency, it's velocity, it's action. Okay, electric charge is something we could deal with, but these are not something one thinks about when forming a system of units. the traditional base units will still be there, they just won't be base units. So let me try to specify. You have something you're going to measure, a quantity Q. That quantity is some numerical value times the unit in the present SI. You can express that unit as powers of the meter to kilogram, second, ampere, kilogram, etc. In the new SI, the units of that quantity is similar, analogous, except you have the constants in here raised to different powers. The constants have dimensions, so you just have different powers for the constants. So example is I have a bar here, it's a length L, let's say it's exactly 1 meter. Well, in the new SI, this L is an exact number, as it turns out, C, the speed of light divided by the frequency of that cesium atom. It's analogous. We have freedom to choose which set of constants we're going to use. Here's a set of constants from the 2010 adjustment. We could have chosen the gravitational constant as to be exact instead of the Planck constant, because this has mass in it, one of its dimensions, as it is Planck. But G is one of the more poorly understood fundamental constants, and it would be a bad choice to choose that one. That's a different story. So one could, if you remember what I told you about how the SI was evolving and adopting exact value of constants in the present SI, you could say all we're doing, we could take the present SI and rewrite it in terms of the proposed new SI when we just have these invariants of nature. If you temporarily give the international prototype a kilogram the status of an invariant of nature, you just have the cesium and the speed of light already are defined. You say IPK is just 1 kilogram. This is already defined. The triple point of water is 273.16 Kelvin. The molar mass of carbon-12 is exactly 12 grams per mole, and the candela is 683 luminous per watt. And all we're doing is taking the 4 in the middle and swapping them out for H, E, K in sub A. And you're going to say, so what? Why are we going through all this? There's some major advantages to going to the new SI. The first one is we do get rid of the IPK, the last remaining artifact forming the foundation of our system of units. Here's a schematic of the present SI. So you have, again, the 7 base units, and then all the derived units within the HI, within the SI. So this kilogram, which is defined exactly as 1, if it changes, well, by definition, it does not. What happens is everything related to it changes, including this volt, which I'll get to, we can measure very precisely with quantum standards. So here's the kilogram, the official IPK. It's in a vault. It has official copies, 6 of them. And in order to realize this thing, once a year, 3 keys are brought in, and they unlock the vault. They open up the vault door, and they go, yep, there it is, and they close it. And that's how they realize the kilogram. It's not really accessible to everyone, anywhere, anytime. It is not stable, since its creation back in 1889. It's actually come out 3 times, I'll get to the third, but twice, once after World War II, and then right before the 1990 assignment of the conventional electrical units. But you can see this horizontal axis, by definition, is Lagrange K, the international prototype of kilogram. Its official copies and some national standards. And the ensemble of all the others are going up with respect to the kilogram. This is a relative drift. You don't know what the drift is in terms of absolute mass or absolute terms. This is comparing a rock to a rock. It's not accessible because in between these, it's the world flies blind. What the BIPM has are working standards to calibrate other national mass standards, and that's what they use. But every 50 years or so, these working standards get calibrated against IPK. Because of the redefinition effort, they pulled out the IPK and its official copies and measured them all with respect to one another, and they agreed very, very well with the values that they got back in 1991. What's not shown on this graph is how well everything in the vault, the IPK and its official copies, are with respect to the working standards. And it turns out there's a shift of roughly 35 or 38 micrograms between what the whole rest of the world was using and what was in the vault. And that's cause for a lot of consternation and conversations at the BIPM and other NMIs at the moment as we go forward with redefinition and what caused the drift. Other advantages is that the SI inherently you can scale orders of magnitude without any uncertainty by using different technologies, different equations which that same constant plugs into. So, time of flight, you can measure distances on the order of 500 million meters to a part in 10/11th, lunar ranging. It's a time of flight measurement, just like the old definition. You can also take it and use it, the wave-like nature of light, and do interferometry and measure, a fifth of a nanometer to 5 parts in 10 to the ninth. This is, you're using optical interferometry along with X-ray crystal interferometry. So you're scaling 18 orders of magnitude using exact value of speed of light, no uncertainty with this as your universal measure. You're not stuck to one value. You're not stuck to like 1 kilogram. You use this constant in different equations of physics. I'll get into it a little bit later, but you can use a watt balance to realize a mass from a Planck constant at the kilogram level at 2 parts in 10 to the 8th. Or you can do atom recoil measurements, absorbing a photon and through energy momentum conservation, spitting it back out, measuring the frequency difference. That's up in here, down there. And you can measure the mass that turns out this is either cesium or rubidium results. So it's 10 to the minus 25 kilograms, and that measurement's done at 2 parts in 10 to the ninth. So you're going 25 orders of magnitude, no uncertainty with this type of system of unit. What are the impacts? Well, along with defining these constants as exact, as they relate to other fundamental constants, physical constants, they are either zero in the uncertainty in the new system or greatly reduced. In particular, our electrical standards based upon the Josephson constant and the von Klitzing constant go to zero because H and E go to zero. And most of these small mass, particle mass, go down and are limited by the uncertainty of alpha squared and, in a lesser extent, the uncertainty of the Rydberg constant. The fine structure constant is dimensionless. It will remain. You can't assign a dimension to it. It's dimensionless. There's no uncertainty in energy conversions. This was kind of interesting to the folks at Fermilab. They measure things in EV, but if you go talk to people doing Raman spectroscopy, they talk in inverse meters or inverse centimeters. And if you do energy conversions and you're actually in the SI, you'll have to assign this uncertainty to it because you're going through the uncertainty associated with relating that 1 kilogram all the way down to quantum levels. So these energy conversions go down to zero. You can compare these different types of energies with no uncertainty. There are losers. Losers. There's a conservation of uncertainty when we do this. So here are those 4 or 5 constants I showed before. The mass of the international prototype of the kilogram now will have an uncertainty. It will just be another artifact with an uncertainty attached to it. The permeability and permittivity of free space so that your system of units are not over-constrained have to then have an uncertainty, and this will be the uncertainty in alpha. The triple point to water will have a relatively large uncertainty. The rest of these, but as far as thermometry is concerned, this is the only place within the temperature scale where the uncertainty in the new SI will be higher than from the present SI. The mass of carbon-12 will have an uncertainty associated with it, but the chemists really measure mass ratios or amount of substance ratios, and they don't really, I don't want to say don't care about mass, but they measure ratios very accurately to below a part per billion, but they don't measure mass directly. And if you wanted mass directly, you would have that uncertainty attached to it. Let me back up to the electrical standards and the impact. And I got to go back to 1990. Actually, 1962, when Brian Josephson predicted that the Josephson effect across a Josephson junction. So you have a superconductor, 2 superconductors with a barrier in between the two. And if you irradiate this barrier with a microwave frequency, then they'll create a voltage that's directly proportional to that frequency and H over 2E. Exactly. So this is a voltage to frequency converter. Now the voltage, depending on your frequency you're radiating with, the voltage is like tens of microvolts step. Because this is a wave boundary value, you get different values. You can go through different steps. But to really scale up, you then put about 300,000 of these junctions together, and then you can go up to plus or minus 10 volts, switching in and out some of the individual Josephson junctions. So we have a voltage, a quantum voltage standard based upon fundamental constants from frequency. Frequencies are measured very, very precisely. Likewise, in the 80s, Klaus von Klitzing discovered the quantum Hall effect. Just a quick reminder of the Hall effect. You have a current flowing in a conductor with an orthogonal magnetic field. That's going to create a Hall voltage, and that's kind of shown down here. So, as you increase the magnetic field, your voltage goes up. Now, for very, very large magnetic fields at very, very low temperatures, and if your Hall bar is two-dimensional, meaning it has a two-dimensional electron gas, then this Hall voltage becomes quantized at various steps. And that quantization, the ratio of the Hall voltage to the current that's flowing through there, is directly proportional to the Planck constants over elementary charge squared. So we have a quantum resistance standard. From these two discoveries back in the 60s, 70s, and 80s, it was recognized that we want to use these quantum standards because they are highly invariant and accessible to everyone, anywhere, anytime. So in 1990, what they did is they took the available data within the SI trying to measure the von Klitzing constant and the Josephson constant, and they assigned a value, that's this dotted line here, gave it an exact number. They didn't call it KJ because these are going to be outside of the SI. These are the conventional electrical units. It's called KJ90. They gave it an exact value. Likewise with the ohm, they took hard-to-do measurements and got the best value, and then assigned exactly a RK90, a value for resistance for that highly precise quantum standard. So these units are outside of the SI because it would be over-constrained if we define these within the SI. But with the new SI, they're coming back in. And unfortunately, we have new data, more precise measurements of relating von Klitzing constant to alpha and Josephson voltage measurements. So this would be the shift from the 90 units to, for the volt 90 to the SI volt upon the shift. This one's pretty large, it's 100 parts per billion. Quite a few customers are going to see this. Anyone with a Josephson junction array can measure down to a part per billion of 10 volts or a tenth of a part per billion at 10 volts. So a lot of our customers, Fluke, Agilent, instrument makers, are going to see this shift, and it's up to NIST and other MIs to communicate this to them as we did in 1990 for various shifts. And one thing I got mentioned is that the whole world, almost all electrical measurements are based upon these 1990 measurements. Almost all electrical measurements are. So a big one is in the power, but by the time we get to a watt for commercial instrumentation and application, even though this is almost 0.2 of a part per million, that's somewhat within the noise of the most accurate measurements. And it should be noted there was an assigned uncertainty if during the assignment of the conventional electrical units, when you wanted to go from the 1990 units to the SI units, the volt 90 to the volt SI, plus minus 400 and plus minus 100, but no one really cared. We were all just in the 1990 units. With the redefinition, the quantum electrical standards will now become part of the SI. So communication, general public. We're all powerful, we're changing the systems, and then don't pay attention to the metrologist behind the curtains, we know what we're doing. That's probably the wrong message to send. The real message to send is that your bathroom skills and your grocery store skills, nothing's going to change. You're not going to notice. Let's go back to our man with the stick performing a precision measurement, and let's go look up the Major League Baseball official rules. So this spherical object can weigh no less than 5, no more than 5¼ ounces of avoirdupois. This is a 5% deviation of that ball hurling at them at 40 meters a second, or 90 miles an hour. And if we're going to, modify the definition of that sphere at a 10 parts per billion, let's just be gross about it, okay? I don't think it's going to affect his ability to make this precision measurement. So nothing really is going to change for the general public. And in fact, the archives of 1799 are more than adequate for almost all daily measurements and weights today. Okay, so why are we doing this? Let's go back and think about when they were doing this. People were starving in Paris. They didn't have any bread, and the natural philosophers were worrying about this to, I don't know, maybe 7 digits or something. Okay, why were they doing it back then when the population was worrying about feeding itself? That's sort of where we are now, where we're going to 10th, 11th digit when the general population is catching up at the 6th and 7th digits. We're trying to stay ahead. We're also trying to communicate. NIST has formed, this is a what do you call it, a website under construction. We're trying to tell you about the redefinition. Now, remember I said there are no base units, but we're just used to the base units. So we're phrasing this in terms of the traditional base units, the ampere, Kelvin, kilogram, and mole. Those are the ones that are going to change. Right now, only the kilogram has been populated. You can go there, you can look at the past. You can look at the present, artifacts. And you go to the future, and you can get a description here of how we're going to realize mass off a watt balance. And if I'm lucky, this will actually work. So this is made by Jenny Lee and with the help of Kurt Suplee and Sean. Mind you, this is for the general public.
An ordinary beam balance works by adjusting the amount of mass on one side of the beam so that its weight exactly balances the weight of a test mass on the other side. Gravitational force against gravitational force. A watt balance, for all its sophistication, does basically the same thing. In this case, however, the force that balances the weight of the mass is not gravitational, but electromagnetic. This force is produced by a coil of wire that is suspended in a strong magnetic field, created by stationary permanent magnets. The watt balance lets researchers determine the mass of an object indirectly by determining 2 quantities: the strength of the magnetic field and the current running through the coil of wire. It does this in 2 separate measuring modes. The first, called velocity mode, uses an electric motor to move the coil through the magnetic field at a constant velocity. This movement induces a voltage in the coil that is exactly proportional to the field strength. Measuring the voltage indicates the field strength. In the second mode, called weighing mode, an electrical current is run through the coil to turn it into an electromagnet. As the coil's field interacts with that of the permanent magnets, an upward force is exerted, proportional to the current, which can be measured. NIST's new watt balance uses a wheel instead of a balance beam. Attached to the wheel on one side is the coil and a platform for the test mass. On the other side is the motor that moves the coil in velocity mode. Both the coil and the motor are surrounded by metal enclosures. In velocity mode, laser sensors track the coil's motion using a technique called interferometry. This detects differences in position as small as a fraction of the wavelength of the laser light. As the motor moves the coil, the interferometry system ensures that the coil's motion remains perfectly constant. That constant velocity makes it possible to calculate the strength of the magnetic field. In weighing mode, a test mass is placed onto the platform on the same side of the balance as the coil. An electrical current runs through the coil, producing an upward force that is proportional to the current. By carefully adjusting the current, the upward force is tuned until it exactly offsets the weight of the test mass, and the system reaches equilibrium.
So let me expand on that the basic description, and let me go into why it's called a watt balance, and how you get a mass out of the Planck constant. Here shown are the two modes, and simple one-dimensional analysis of balancing the force equation. If you write this down, you can get the quotient of the mass times gravity over the current in the coil equals what they were calling the magnetic field, or this magnetic flux integral, or what we just call the BL factor. In the velocity mode, you measure the velocity and the voltage induced, and you form the quotient of voltage to velocity. That equals the same BL factor. And so when you combine these two results and invert them, you get mechanical power, MGV, equals electrical power. All right, now what's somewhat important, and one of the tricks of the watt balance, is that this force mode is done when there's no mechanical motion. You cannot have frictional forces or dissipative forces in your balance, otherwise it would kill you. And in the velocity mode, likewise, your meter reading the voltage has an incredibly high input impedance, so there's no electrical dissipation of energy. So this is really a virtual watt equation, but this is why it's called a watt balance. If I rearrange it, the equations in terms of mass, I have a BL factor, I stick in my voltage in here. Now I also rearrange my current in terms of voltage divided by resistance, because no one measures current, they measure voltage and resistance due to the quantum standards. I stick the quantum standards in here, I pop out a Planck constant, some integers, some frequency measurements in gravity and velocity. And this is how we relate the Planck constant, an exact value of Planck constant, to the future realization of mass. So to further educate everybody, we made an army of Lego watt balances to demonstrate the principle. This base here is roughly 40 centimeters or something. And we really did this. We submitted a publication, and we give you the parts list if you want to make one of these. We describe how the principle of operation and how to calibrate your various sensors. And if you want to contact Leon Chow, we will easily hand you over the software that runs this. This total cost was over $600 for us, but if you bought a cheaper DAC board, you could get it down around $200. And this is we've taken this to the science shows, and it really helps. The kids love it, the educators love it. It gives you the flavor of balancing electromagnetic forces with mechanical forces. I talked about the scaling aspects, and the metrological and scientific communities certainly see the advantages of the scaling. But for manufacturers, this may take a little bit more time. Let's go back and look at how mass is disseminated today. We start with a kilogram because that's the definition. They take they divide down by a set, and then they get to 500 and 200. They divide these down again to go to 50 and 20, and they continue dividing down. They have to come off of this value because that value is the definition. And if you look at the uncertainty, so a kilogram, this is for stainless steel. Okay, so this is 2, 3, 4 parts attenuate, depends on the NMI. And as you go away from that 1 kilogram, not surprisingly, your uncertainty grows as you divide this down. At every transfer, you're going to pick up more uncertainty. And so at a milligram, you're getting down here, and certainly at, I don't know what that is, 500 micrograms, you have these wires that are kind of the size of dust. And this is a really painful way. It's the way we do it now. With the new SI, we can make small masses through small force measurements, taking advantage of electromagnetics. In this case, it's electrostatics. We have a capacitor, a cylindrical capacitor, that we measure the capacitance gradient. When we move it up and down, it's hooked to a very precise balance. We can put a small mass on here. And then when we apply a voltage, we would get a force that balances the mass of the gravity, mass times gravity. We've realized 20 milligrams. This is the NIST electrostatic force balance. Here's that concentric capacitor electrode right here. We've realized 20 milligrams to roughly 20 parts per million. That's what you can do with dead weights. And just recently, with some upgrades, we've done 50 times better. So if you're a balanced manufacturer of small masses or or disseminating small masses for various industries. One is pharmaceutical, another is thin films for the semiconductor electronics industry. You could have one of these small force measurements and a single digital multimeter, and you could disseminate your mass off of that, not having to go back through the long chain. And then with that single digital multimeter, you could calibrate that once every 5 years or so, instead of constantly sending your masses back and disseminating down all the way. So we're on the road to redefinition. Here's the various, I haven't bored you with all the politics behind this and all the interests and the various discussions, let's say. But this is a roadmap by the Consultative Committee of Mass put together back at their meeting in 2013. Here's this extraordinary calibration of the IPK that's kind of finished up here and has some results that is causing a lot of conversation. We have the watt balances that are going to be publishing results here in the year 2016. Various meetings. Here's the CIPM meeting that we're targeting, that they will then inform CODATA to do a special adjustment to provide the actual values that will be used to define it as exact. And we're all targeting this 26th meeting of the General Conference of Weights and Measures in 2018 for redefinition. So in the far future, after we made this new SI, what's the next new SI? Let's see, we got velocity, this is length over time, and this is frequency, cycles per second. It is possible that we could replace that with a better value of the Rydberg constant. There are experiments out there that are creating exotic Rydberg atoms so that they can measure the Rydberg constant. Right now it's like part 10 to the 12th uncertainty, and they need to go a modest factor of 100 or 1,000 to compete with the cesium clock's uncertainty. So that's one way to go for changing the SI. Unfortunately, though, for the Rydberg proponents, the new frequency standard from optical clocks is probably going to be our new time standard, because optical clocks now are at parts in 10 to the 18th. So these are the far future changes that possibly will take place. So in summary, the SI will continue to evolve as we gain new knowledge about our physical world, as we make physical measurements. Fundamental constants are true universals of measure available to anybody, anywhere, anytime. And we are expecting to redefine in 2018. And since I have a little bit more time, I'd like to show you the construction of the 4th generation of the NIST watt balance. It's called NIST 4, and this is how hard we work. So here's the magnet. We're splitting it. We have to pull the magnet apart to put the coil inside of it, because it's all encased in iron to control the magnetic flux lines. And yeah, we worked that hard. So the magnet splitter goes out. Here goes the magnet. We're putting that in. We're now putting the platform on top. So here comes the ELF. Extremely low flexure. We make some vibration measurements, take a look at the modes we just created by putting all this mass on these 2 long beams. We got a lot of harumphers, suits and ties come in saying good job. What are we doing now? We're putting the rods in, attaching the coil, putting the bands on our wheel, loading it on the knife edge. We're now splitting the forcer on the other side that allows us to control position, velocity. More vibration measurements. Got our laser system going in here. Okay. Bringing in the electronics. I'm ready to give you a kilogram. So thank you.
You have no idea how important this is. Really, it's really important. We have time for some questions. There are 2 runners with mics. If you'll wait till the mic comes to you, and when it does, please stand up, state your name, and tell us whether you're a member or just visiting. We'd appreciate it. So we have the first question right there. Please hold your hand up for a while so the microphone can get to you.
Okay, hello. David Rosen, I am a lifetime member.
David?
Could you talk about the plans of protocols and experiments that NIST would use to determine whether any of these universal constants are changing over the time span of decades? I mean, it's not likely, but it's just possible they might change. So, or even over space, over distance they could change, right?
Right. So the flippant answer is that we define them constant. By definition, they're constant, just like the IPK is constant. Specific measurements by NIST to look at the possible time variation of the constants comes in comparing two different extremely precise clocks and looking for the time variation of the fine structure constant. So one clock is heavily dependent, its transition is heavily dependent on alpha and the other is not. And you beat the two together. And I believe that the optical clocks are at parts in 10 to the 18th. Within that level, there's no evidence of time variation of the fine structure constant at this time. Now you can do astronomical observations and ask what was alpha back at the beginning of the universe and all that, and there may be some evidence, but then there's some debate about that. But the measurement that NIST is doing and others are, they're looking for a time variation of the fine structure constant. Now if that changes, I think it'd be exciting. It would be good for business because that would be knowing something about the universe that we didn't know before. That there are discrepancies out there amongst measurements that have not been explained through an error in the measurement or an error in the theory, and that really is pointing towards exciting possible new physics. Usually someone's made a mistake. Almost always someone made a mistake.
Monitoring unitless combination.
Yeah, the fine structure it's given to us. It's 137 or 1 over 137.00 something, and you cannot assign that. You measure it, and if you find it has a time variation in it, then one or some or all of the other constants are changing, and that would be exciting because you wouldn't know what combination would be.
Exciting.
You want me to continue?
Yeah,
with
go
the
ahead,
one?
Brian.
My name is Rudy Krutar. I am a member. And my question has to do with the definition of the meter in terms of the speed of light. It's like a little bit over 1/300 millionth of a light second. And we use that with the speed of light, we end up with the speed of light as a constant 1 light second per second. Okay, which is a tautology, right? And I believe that the reason the universe is accelerating in expansion is that the speed of light is changing over cosmological periods, and we end up with the meter shrinking, and therefore the number of meters to the event horizon has been increasing until it's now like 13 billion light years away. The other problem is that with the speed of light, they're not additive. If you have 0.6 c plus 0.8 c, you don't get 1.4 c. You get something less than c. And how do you deal with non-additive units for non-additive measurements?
Let me try to answer that in terms of the philosophy of when we adjust the fundamental constants, when the task group fundamental constants does an adjustment. There quite possibly could be variation of the fundamental constants, but in order to get your best value today, we accept some of the theories to be true and valid. That would be QED, that would be CPT violation, and that would include the speed of light being constant within our measurements. There are no measurements that I'm aware of that points towards, that are valid, that points towards a time variation of the speed of light.
I'm Bob Hershey. I'm a member. For your next version of the second, you have it in one part in 10 to the 18th now. What are you thinking of to get it to an even better second.
Well, I'm not in the time and frequency division. I don't know where they're going to go beyond the silver clocks. There's other candidates for the optical clocks. Beats me. I mean, that's the tour de force getting down to that level, and then it's provided a vast explosion of technology and use. I mean, everyone's driving around with the voice talking to them in their car, telling them exactly where they are and where they should go, whether you want to go there or not. So that's all from the precision of time and frequency measurements. I don't have a good answer. I don't know what's beyond the new SI. I'm kind of looking at in the future, and I'm ignoring the political battle of, my clock's better than your clock, we should use this element and not that element, and it will take time. It took the speed of light to be defined, even though it was measured, and they knew that this is the way to go, and the krypton wavelength had problems. It still took them 10, 15 years to agree. It's a decision by committee. It takes time.
I'm interested in your concept of
Name?
I'm Timothy Thomas. I'm a member of the society. I'd like to ask a question about conservation of uncertainty that you mentioned. And I'm assuming that means you can't cancel one uncertainty with another uncertainty. But I'm not sure what it means. And then secondly, I'm wondering if the Bureau of Standards has got a standard for uncertainty, a way in which you're officially to measure it.
Okay. Two questions. I should be a little bit less flippant with that question on the conservation of uncertainty. It's just so we have uncertainty, 44 parts per billion on mass of fundamental particles, and that comes from scaling from the kilogram down to the elementary particles. And so you can imagine if you started with an exact fundamental particle, you're going to get that same uncertainty going back. So that's all I mean by the big mass now is going to have that uncertainty as you try to take quantum physics equations and relate it to macroscopic things that we deal with every day. That's where the new technology and the new frontier of measurements are. It's in the nanoscale regime, and it's not an ampere, it's electron per second, or a fraction of electron as it fluctuates on a thin membrane. So the second question was standard for uncertainties. Yeah, that's called the GUM, Guide to Expression of Uncertainty in Measurements. And actually, that's a good question because that's being revamped and revisited and rewritten here within the statistical engineering division at NIST and with the BIPM. For co-data, when we do uncertainties, we try to keep it, I want to say simple, well, so I can understand, but it's simple for everyone else can understand. We do least squared analysis. We use a mechanism so that we can have an input covariance matrix to take in consideration of the relationships of various experiments, because they sometimes use the same part of the apparatus, and so you just can't root sum square the uncertainties. And it's really straightforward least squares analysis. There's other analysis you can do. You can do Bayesian statistics, but then we want to just keep it garbage in, garbage out. You can just stare at the data saying that ain't right. You don't need to apply a tool to it.
Let's have here and then you.
John Greenhill, I'm not a member, but thinking of becoming one.
Excellent.
Does NIST have a position on what's called leap seconds? The definition of a year is GMT and the universal coordinated time, but the time is measured so accurately we know the Earth is slowing down and the number of seconds in a year is going to change. And so does NIST have a position on what the definition of universal coordinated time will be?
I'm going to have to say I don't know if NIST has a position. I'm sure there's opinions on that. My understanding is that I don't know. I think that there's a kind of a mutual agreement at the CC time and frequency TNF, where they will adopt leap seconds when they need to because of this effect. I don't know how. There's a few of them out there in the past a couple decades, but That's actually decisions made at the CIPM, CGPM, level, being advised by the Consultative Committee of Time and Frequency. So it's not just NIST. We may have it a position, but I don't know what it is. I think we would adapt the leap seconds when we need them, because theirs slows down, goes faster.
My question, my name is James Griffin, and I'm a guest. My question is sort of about the abstract properties of the new SI. And I'd like to ask, suppose you found yourself in another universe suddenly, you and your whole team, with different constants for C and all of the fundamental constants of physics. The multiverses claim that there are an infinite number of such universes, and they all may have all possible values of all possible fundamental constants. Would you guys be in business in that universe the next day, or would you have to start over?
I think we would be in business. Now, okay, you actually, that's a wide, it's such a wide open question, but let's assume, let me simplify the question. Let's assume that someone actually wanted from beyond our planet really wanted to talk to us, okay, wanted to visit us, and they wanted to make a spaceship for our bodies and whatnot. We could give them information how to make the spaceship. We could tell them, let's assume that they're using the same laws of physics. I have to make that assumption. We can give them information. This is our length measurement. You take light, and it goes so far, in this amount of time, that's our meter. Now build your spaceship by X meters and whatnot. We can tell them what our time reference is. We can tell them what our mass standard is through the fundamental constants. They can, right now, we would have to, for mass, we'd have to take the kilogram and throw it at them, which would be active war. But we could give them information, they could build a spaceship, and this is why it's available to anybody, anywhere, anytime. Now, if you're going to change the laws of physics and the speed of light is now 1, I don't know.
I'd like to keep the laws the same, just the constant.
Well, they go hand in hand.
No. The mathematics of the laws of physics have constants in them. And when you change the constants, the mathematics of the law can retain the same structure. And that's the multiverse that I'm thinking of. Maxwell's equations
Sorry.
have C in them,
Yeah.
but if C changes, then all the behavior of light changes, but the law of Maxwell's equations are still good.
So you're changing the speed of light.
Yeah.
Yeah.
My understanding of the multiverses that astrophysicists envisage are that they have all the same laws of physics, but different fundamental constants. And since you're building your system on fundamentals of constants, I would have hoped that maybe if you landed in one of those universes, you could say this is just as good a set of standards as any, because you just put different numbers in for the constants, and then everything in this new universe, which looks very different because the constants are so different, but all the laws of physics are the same.
Well, okay. I don't know if I can answer that.
Maybe this is one for after the lecture discussion. But I gather you would suggest a universe in which, instead of having gravity with a very, very weak constant and electromagnetism with a large one, you'd have gravity with a gigantic constant and electromagnetism with a weak one, which would make for a very strange place, maybe. But let's take it to, I think we have a question back there.
Yes.
Go ahead.
I'm Jay Abdallah. I'm a guest here tonight. It's going to be hard to follow up that amazing question, but my question was just, what do these changes mean for students of chemistry, physics, and the other natural sciences at the undergraduate level?
Right. It's going to be harder for the educators to describe how we realize mass. And I can guess or project that physics will still be taught how we, you introduce, Newtonian mechanics, and then you go to electromagnetics before you go to quantum physics and, special and general relativity. So it probably will still be taught through the traditional base units. And that's a hard question. I mean, we were trying to show how our standard of mass is related to the Planck constant. It's not defined by the Planck constant, but it's related to the Planck constant, the speed of light in a second. We appreciate any feedback how to better describe that. It will be challenging. There's no way around that. We're using quantum physics. We're using constants that we've measured that aren't just artifacts that are this long and that big. So, sorry, that's not a very good answer.
Irreverently, I can almost guarantee you that it will mean that you'll need a new textbook and it will be more expensive.
Yeah, that's right. So,
I'm sorry, does that mean that the material is outdated necessarily, or the units?
well, my textbook had the MKSI system in it, and that was out of date when I had it because it didn't have the Candela I mean, it takes a while for that stuff to get in the textbook. It won't be as simple. The appendix in your physics textbook that just lists the SI, that's going to get more complicated.
Aside from the mathematics, and which are developing at a very rapid pace, have you given some estimation as to how long it would take to re-educate the educational system and the population to be able to understand and use what you have just described?
No. A while.
Come on, he just designed this wonderful watt balance. What more do you want?
We were trying. I mean, I'm sorry, again, I'm being flippant. There are several of us at NIST trying to write articles. One of them is Bill Phillips and Peter Moore trying to write, in conjunction with a high school physics teacher, how would you introduce this? I'm trying it with another colleague. Our method's a little bit different, and we'll see. Will they succeed? Will people get it? As a physicist, after knowing some of the, I've drinking the Kool-Aid. I'm educated in physics, but try this for your senior high school physics student or undergraduate, one who is not has yet really learned that there's units being used. They just know the laws of physics are being taught, and tell them, okay, how we really make physical measurements. We know that there's fundamental constants that have dimensions to them, and we accept these constants to be constant within our universe, and they have dimensions, and we take a set of them so that we can, an unconstrained set, but that spans all of our physical measurements, so that we can take a combination of them to get whatever we want, a length, a time, a second. And to me, when you just rattle off H equals that and has units, C equals that, somehow that appeals to me. Just the fact that you can take a set, and it doesn't matter what the set is, it does matter that the set of constants span the physical measurements that we make. And they can't be over-constrained. You can't have the Rydberg and the speed of light and a cesium clock in your system. But try that. To me, that makes sense. I don't know. I tried this with a couple undergraduates that say, that makes sense. You're not knowing the previous definitions of the present SI. It's going to take time.
Question.
Hi. I'm Lauren, not a member. This dovetails a little bit with his question about being outdated. My husband is always way more excited about 2.0 of whatever it is, because 2.0 means they got the kinks worked out.
The education.
They already made all the mistakes. So I'm wondering if with this new system, there's something specific that everybody out there is like, yes, we could do this now. And then as a follow-up to that, why wait until 2018 if there is something?
Let me answer the last one. Personally, I thought we should have redefined back in 1990, but that's because I'm from the electrical community. Why we haven't redefined is this conservation of uncertainty going into the mass community, and they're very nervous that we may choose the wrong value when in fact, any values will in my biased opinion, would do. So it is a decision by committee, and that's why it's taken so long to 2018. But the momentum has built, and the data have gotten better, to redefine the mass in terms of the Planck constant. That was one showstopper. That's one massive conversation. The other was a while back in 2008, 2010, was deciding which set of fundamental constants to use. Now, the electrical community wants E and H for obvious reasons when you look at the Josephson and von Klitzing constants. But some other groups want the Planck charge because it's pure or something, even though nature gives us E to measure, not the Planck charge. So this is what's taken time. Your first question was, 2.0, what kinks have we ironed out?
Not what kinks have you ironed out, but like what is the community excited that this new system is going to allow them to do differently?
It goes along the line of the opportunity to realize any value of a unit, the scaling aspect. You don't have to go to a kilogram. The watt balance at a kilogram is an intensive effort. And there's other NMIs out there that don't have the resources to pour into a watt balance. But what they're missing is that you no longer have to go to a kilogram for your mass standard. You can go to a gram. A gram watt balance sits on a table. It's like the Lego watt balance. And if you do a little, be very careful with your precision measurements, you can probably get that thing working at part in 10 to the 6th, maybe parts in 10 to the 7th, which is far better than taking the IPK and then disseminating down to the 1 gram. So it opens up opportunities of making measurements and scaling over 24, 25 orders of magnitude without any uncertainty coming from your system of units.
So it might be fair to observe that one thing this system does, you pointed out in one of your slides, is the comparison between the working examples and the standard that's kept in the vault in France, having drifted apart, which is not going to happen when the new system is instituted.
That's right.
So it means that anybody, anywhere, following the prescribed methods can have as reliable a standard as anybody, anywhere. And so there won't be those kinds of drifts, mistakes, and incompatibilities. I wanted to ask a question. Can I ask a question, Carl? It's a kind of follow-up to your question. And the question is, can you point out a few things where the increased accuracy and reliability and reproducibility is going to make a difference in, say, what semiconductor manufacturers can do, or what cosmologists can do when they're trying to coordinate the signals acquired from 1,000 different radio telescopes in the desert, or whatever you care to, but you point to some things that people will be able to do when the new system's instituted because of increases in accuracy and reproducibility that we are only thinking about right now.
That's a tough one.
Is that a tough one?
It shouldn't be. I've kind of already used that answer, and it's so semiconducting. It's more in the exploration of new physics, and it's the measuring the single electron, not just an ampere, but just electron per second, or a fraction of a charge. In that measurement, I don't have a good example of how that then can compare to a totally independent measurement comparing through the SI, but that measurement of the electron charge, if you're doing it, oh yes, I can. Recently, there was a measurement of, very precise measurement of the mass of the electron. This is Klaus Blom at Mainz. And they tried to publish the first title was, the most accurate measurement of the mass electron. And that implied measuring within the SI, and they're not. They're using atomic mass units. So with this redefinition, they can actually, with their very low uncertainty, say that they're measuring the mass electron. They had to convert that into the relative atomic mass to this arbitrary exact value of the atomic mass unit. So this allows people to compare directly within the SI of fundamental masses of fundamental particles. I don't know if that was a good answer.
That was a very good answer. Carl, you had one last question. Microphone. It's on.
Carl Merrill, I'm a member of the society, and if I understood what you said correctly, there, you have that standard weight in Paris, but there are additional copies of it in other places, and they've all gained mass over this period of time? So is there any speculation as to that? That's one question. And the second question is, with that velocity wheel, gravity plays a role in that because of the way it's set up. You're moving it up and down in the gravity field. So does that have any effect at all?
No on the latter, and the first question was about, I'm sorry, what the...
How did the working mass?
Drifting.
Yeah. Right, so I showed you the vault, there's the IPK, and there's 6 official copies made at the same time that have been sampling the same paint coming off of that inside of the vault, and they actually got a new vault. So there's 6 of those, but at the same time in 1889 and before, they were also making national standards for the signatures of the Treaty of the Meter. NIST has K4 and K20, it's just the numbers. So various, Germany, PTB, the National Physics Laboratory in England, they all got copies because of their initial signatures. All right, so what I showed on that drift graph were the official copies and then some of the national standards that have existed since 1889, okay? Now, what happened is that at the BIPM, those official copies aren't touched. There's another set of working standards that the BIPM uses that every 50 years they'll compare those to the ones in the vault, but then those are what the copies from the countries are compared to. And it's the things in the vault at the BIPM versus the working standards that had a 35, I don't forget which way it went, 35 microgal shift overall for both of them. And that's causing a lot of consternation and trying to figure out why. They talk about where they introduced some of these new precision mass balances, comparators in 2008 or so, and so they saw a correlation in mass loss due to the number of times they were wearing with this one balance. But there's also this equation of mass gain, because the official definition actually is it's the mass of the IPK right after it's washed. So they take it out, and the first they compare it against the standard, and then they spray it with distilled water and alcohol and rub it with a chamois cloth with a hand, and then they weigh it again. And that's the definition right after weighing. Actually, they wash it twice. Sometimes they wash it 3 times. They should only wash it twice. And that's the official definition. And so the various hands that have been washing it have changed throughout the 120 years. And so there's a model being applied to that. And it really, you're dealing with an artifact. You know, there's no prescribed equation that you can write down and say, no one's proven this equation wrong. You know, that came back. Gravity. So our travel is 10 centimeters, and gravity changes pi parts per billion per centimeter. So it's going to change by 30 parts per billion. But we move it, that's in the velocity mode when we're measuring voltage and velocity. When we're measuring the force, that's where the gravity comes in. We measure at a set point, and that point we try to characterize very, very carefully what the local acceleration of gravity is. I like that question because that's my contribution really to the project, is measuring gravity. I can answer that one.
Well, thank you very much, David, in appreciation for this talk.
Thank you.
We're presenting you with this copy of the announcement of your lecture, signed by the members of the General Committee on behalf of the membership of the Philosophical Society.
Thank you very much.
Thank you very much for
Thank
a
you,
wonderful and informative talk.
Thank you, Al. It's been very enjoyable.